Let's do a couple problems where we talk about continuity a little bit more. So, quick review of 1.1. Informally, a function is continuous if you can take your pencil and follow the entire graph without ever having to lift up. That's a continuous function. We have three main types of discontinuities we talk about. We have a jump discontinuity, a hole discontinuity, and an asymptote discontinuity. The only one of those that is a removable discontinuity is a hole. Jump and asymptotes are not removable. So we're going to talk right here, discuss the continuity of this function. So if we look at this function right here and plug in 3, I get 3 squared minus 2 times 3 minus 3. Here, let me write this over to the side actually. 3 squared minus 2 times 3 minus 3, all over 3 minus 3. So 9 minus 6 minus 3, that's going to be 0 over 0. Hey, this is our indeterminate form, which means I can simplify this. So I'm going to do that over here. What I'm going to do to simplify is I'm going to factor that numerator. So I need to factor this to x minus 3 and x plus 1. So I have my x minus 3's cancel, and I end up with x plus 1. Now, because these cancel, that tells me I have a hole discontinuity. So right now, immediately, I know I have a hole discontinuity, which would be removable. So I'm going to write a removable discontinuity at x equals 3. So I have a removable, a hole discontinuity at x equals 3. So this line of this piecewise is essentially trying to fill the hole. That's the question, is at x equals 3, does 5 fill my hole discontinuity? So what we need to do is see, does 5 fill the hole? So what we need to do is find the limit as x goes to 3 of this function, which of x squared minus 2x minus 3. So let's use our simplified version. So now I can do direct substitution. So the limit as x goes to 3 of this first part is 4. But if we look up here, they tried to fill it with 5. So 5 is not going to fill the hole, which means it is still a removable discontinuity. Because they tried to fill the hole with 5, but that's not the right number. Now, however, if this was a 4 instead, then we could check it and say this is continuous because they filled the hole at the right spot. So for number 7, we're asking a slightly different continuity question. We're saying if this is a function and we want it to be continuous. So normally this piecewise would look kind of like this. We have x minus 3, and then we have a parabola. And what they're saying is at this point right here, what would A need to be so that they meet up just perfectly and the function is still continuous? So to do that, we need to look at the limit from both sides. So if I look at the limit as x goes to 2 from the left, if I want to go from 2 from the left, that's going to be this second function right here, x minus 3, because it's from the left, so less than. This one, as x goes to 2 from the right, that's going to be my 3x squared plus a, because that's when it's greater than from the right. From here, I can do direct substitution. So I get 3 minus 2 is 1. And 3 times 2 squared plus a would be 12 plus a. Now the thing that I want to do, if I want these to be continuous, then that means the limit from the left needs to equal the limit from the right. If the limit from the left equals the limit from the right, then it's continuous. So the limit from the left was 1. The limit from the right was 12 plus a. And if I solve that, that tells me that a, oops, sorry guys, I did that backwards, didn't I? Let me go back and fix that. 2 minus 3, negative 1. There we go. Now it's fixed. So a would be negative 13. So if a is negative 13, that means the parabola is at just the right spot so that those two pieces match up perfectly and it is smoothly continuous. In the next video, we'll go through a table and talk about approximating continuity using a table.